This is Physics 1 Experiment 3, example of the calculation of a standard deviation. In your laboratory notebook there is an example of how to calculate the standard deviation of a set of numbers. And basically just a few things about notation. Here we have a set of numbers or numerical values, and I've just sorted them from smallest to largest. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 values there. Now we use the symbol x to represent any particular value, so x subscript I is the general form of notation. So x subscript 1 or x1 is 3.28, x2 is 3.35, x3 3.39, and so on. Now the first thing we want to do is work out the average of all of these numbers. Well, you should all know how to work out an average. You simply add up, get the sum of all of the numbers, and that's what this is down here. 42.07 is the sum of all of those numbers, and that's what this notation means here. That Greek capital sigma sign, sigma xi, simply means add up all of the xi's. To calculate the average value, pretty straightforward high school maths, is the sum of all the numbers divided by the number of values, n. In this case it's 12, and so 42.07 divided by 12 gives us the average value. So 42.07, about 3.506. Now, even though these are to 2 decimal places, I'm going to temporarily have that answer to 3 decimal places, because this is part of an intermediate calculation. Another thing about notation, the x with a horizontal bar over the top means the average value of x. Now what we want to talk about is how are all of these values scattered about the average value. You might think one thing we could do is work out the deviation from the mean. xi minus x bar. So in the first case, well, let's look at the bottom one first. It's the largest number. 3.98 minus 3.506 or 3.51 or 506 is 0.474. So that is how much bigger 3.98 is than that. Again, notice I've gone to an extra decimal place. I know you've been taught in school you should never do this, but this is an intermediate calculation. We only ever round up fully at the end of a calculation, and if you consistently round up in the middle of a calculation, you will get errors in your last decimal place when you finally present the final value. So we're going to go to 3 places. So this is called the deviation from the mean, the xi minus x bar. Each individual value minus the average value. And of course, if it's smaller than the average value, 3.28 is smaller than 3.506, it's a negative number, meaning 3.28 is 0.226 below the average value. And you might think, well, to get a measure of scatter, why don't we average all of these numbers? The thing about the average is there's just as many readings below the average as above the average, and if you add up all of those you will actually get 0. And so that's not really worth doing. You might think, well, perhaps let's take the absolute values of all of these, make those all positive signs, add them up and work out the average deviation from the mean. That's almost what we do, but for deeper reasons in mathematics, what is often done in a situation like this to get rid of a negative sign is the first thing we do, let's square all of these numbers. Now, because they are to 3 decimal places and I'm squaring them, I'm going to take this out to 6 decimal places. Now I know you might say, okay, 3 significant figures there, why am I worrying about 5 significant figures here? We're doing that because as we proceed through the calculation, we do not want to have round-off errors partway through. So it does get a bit long and complicated if you do this by hand. But what's this xi minus x bar all squared? Well, that is the deviation from the mean. So this would be the square of the deviation of the mean. And so what we do is let's add up all of those, which we do here. So that is the sum of the squares of the deviation of the mean. It's just the sum of that column of numbers. Let's work out the average of that value. Now the average of that value would be sigma xi minus x bar all squared over n. So that's the average of the squares of the deviations from the mean. But if this over here was in some particular unit, say that was the distance and that was in metres, well that would also be in metres, but this would be in metres squared. So to make it sensible, to get a sensible result to compare from this average value to compare that to the original data, we need to take the square root of that. So that is the square root of the average of the squares of the deviation of the mean. Or, as an engineer might say it, the root mean square deviation, the RMS deviation. In engineering, with continuous functions, the RMS deviation of a voltage is known as the RMS voltage and so on. It's simply the square root of the average of the square of the deviation of the mean. In statistics, the RMS deviation is called the standard deviation. And that would be the standard deviation of that set of numbers. Now in practice there are two formulae for the standard deviation. One is this one, that's the standard deviation of a set of numbers, and a more common one that's actually used is this, sigma xi minus x bar all squared over n minus 1. On a lot of calculators that will be sigma n. On your calculator, if you're doing statistics, that will be sigma n minus 1. Why use this formula? There's a bit of logic in statistics that says if this is just a subset of all possible measurements, for instance if we measured the height of everyone in a class of 50 people and then wanted to make a statement about how the average of that height varies over the whole population of people in the city, we would really need to use this formula because and the difference between that one and that one is not very big. If n is a large number, like 100, the n there would be 100, the n there would be 99, it's only going to cause a 1% change under the square root sign. There would be a 0.5% difference in the final result. It's almost not worth doing. But with small numbers of values, like we'll be working with 10 values, that will be a 10 and that would be a 9. The difference between root 10 and root 9 is about 15%, 15 or 16%, which means, no, sorry, it's about 2%, and so that would lead to about a 1% variation in the final answer. Anyhow, two possible standard deviations. This is the one we would normally use in science. And so that's what's worked out here. There's another common or older symbol for this standard deviation, sometimes called S. These days it's more often called sigma n minus 1. And so there is the square root of the average of the squares of the deviations of the mean. Another reason why the n minus 1 is there, it's called degrees of freedom. We might have 12 data points there, but there's really only 11 gaps between them, and so that's why there's an n minus 1 there. Calculating that right through, we end up with the final value of the standard deviation of this set of numbers to be 0.177. So, looking at all of that and rounding it up, let's have a look at the final values down here. In the first instance, the average value is to 3 decimal places, all the data is to 2. Let's round that to 2 decimal places now. At the end of the calculation, I write 3.51. So I write 3.51. And then round this to match, or rather I've rounded this up. Since the leading digits are 1, I can quote 2 figures there, make that 0.18. So there we are, 3.51 plus or minus 0.18 is the standard deviation, or the spread of those values, based on 12 readings. This is not actually like an absolute error. Plus or minus 1 standard deviation is just about 2/3 of all values fall within that range. If I go out to 2 standard deviations, plus or minus 2 standard deviations, I should encompass 95% of all readings of a normal distribution. So this means something slightly different to an absolute uncertainty, but it is a good way of describing the scatter of results.